Hello and welcome. In this video, we are going to look at series circuit faults. So this is a series circuit here. We have a 10-volt source. We see that it travels through R4, R5, R6, R7, and R8, and leads us down to ground. And so we can do our expectations first. We can say that our total resistance will be the sum of those, and our current would be our voltage divided by the total resistance. So we can take our total resistance of 220, 1000. Watch out for this 2.2 kilo ohms, right? Make sure you put those all in the same notation. So 2,200 for that 2.2 kilo ohms, plus 140, plus 680. So that's our total series resistance there. We can take our 10 volts and divide that by 4,240, and that's going to be our current in the circuit. And so that is what we expect the current in the circuit to be, and if that's not the case, then we know that there's probably a fault in there somewhere. And so let's measure through that. Let's go after our current first. We'll grab our current probe here and put it at the top. We actually get picoamps, 20 picoamps. This measurement is immediately going to tell us that we have way too much resistance, right? Because we expected to have 2.36 milliamps of current, and we actually got picoamps. That's virtually no current at all. And so let's check to see where that happened at. And when we follow this through, we see that that picoamps turns into 0 amps really quickly, and it stays at 0 amps the whole time. So if these were lights, none of them would be on. So let's check our voltage. We know that in series, voltage should drop. We should have 10 volts at the beginning. We should lose voltage as we go across. That's what our voltage divider equation stated for us. And so we expect a voltage drop across each one of these. Right now we have no current, which means we should not have voltage drop. Right? It's going to just show us where the fault lies. So at the very bottom, we should have 0 volts. And as we move through here, we should see a voltage, but we don't, right? 0 volts, 0 volts. We can keep going across here. 0 volts, 10 volts, right? 10 volts right after R5 and 10 volts on the other side of R4. So R4 does not have a voltage drop. That makes sense because it has no current. If there's no current in the circuit, then we don't get voltage drops. We just get potential to the fault, right? So that potential is going to show us where the fault is. So the moment the potential changes. So from the source, we get 10 volts after R4. So R4 is probably not the fault because we get a full potential all the way through it with no current. And we keep going here and we see that after R5, we end up at 0 volts. So R5 is stopping the potential from traveling to the end of the circuit here. So we know that R5 is most likely going to be the fault for us, and that it is stopping current completely, which means that it is way too much resistance, and so we will call R5 open. It's an open fault. And so let's look on this thing here. It says when an open occurs in a series circuit, all of the source voltage appears across the open, and that's what we saw here. We saw that when we had 10 volts on one side, we get 0 volts on the other side. That means that R5's voltage drop is the entire voltage source, right? And that's what we expect. So let's move on to this next one down here. This one has a different fault in it. It's the same circuit though, so we can still use the same voltage and current values that we calculated there as our expectations. And so we'll say that our current here gets us 2.44 milliamps. That's a little bit more than what we expected, so we must have a little bit less resistance than we expect in the circuit because we have more current than we expect. Right? And we see that that 2.44 milliamps stays consistent through the entire series circuit. That's what we expect. Right? There's one current value in a series circuit. So 2.44 is what we actually have. And we can use that to determine our voltage drop across each one of these because we know that that's the current through there. And once we figure out what our voltage distribution should be, we should be able to spot that in our voltage measurements. So let's measure our voltage drop. So 10 volts, we expect a voltage drop across each one of these until we get down to 0 volts. So 10 volts up here, 0 volts at the end. And we do have that. Right, so now let's just go through each one. So 10 volts, 9.46 volts. So we did see a voltage drop across the 220 ohm resistor. That's good. So we keep going here. 9.46 volts leads us over to 7.02. So we have a voltage drop across the 1000 ohm resistor also. So we can keep going here. 7.02 to 1.66. We get a really large voltage drop across this 2200 ohm resistor here. That's what we expect. It's the biggest resistor in the circuit, so it should have the most voltage drop. And as we continue on here, 1.66 volts. 1.66 volts on the other side of this one as well. So this right here is our first faulty measurement here. We see that we have 1.66 volts on the first side of it, and on the other side of this resistor, we have 1.66 volts still, which means that that one did not consume a voltage. when it should have. Right, so we keep going here. 1.66 volts leads us down to 0 volts at the bottom. So this last one has a voltage drop, but this 140 ohm resistor does not, which means that that one's probably shorted, right? It's probably the resistance that we're missing. And if we wanted to calculate this out, we can just remove that 140 from our total resistance equation and say that, well, without that, what is our actual current that we expect? And it's exactly what we measure, right? We'll round that up to 2.44. 2.44. So our short is in the 140 ohm resistor. And when we look at here, it says a short in a series circuit has 0 volts across it. And that's what we saw with our voltage measurement when it did not drop any voltage from one side of that resistor to the other side of the resistor. All right, let's look at one more here. Move our probes down. So this last one is the trickiest one to solve for. Let's put it in our 140 again. We'll add our 140 ohm resistor in there. So this is what we expect it to be. We'll put our 2,4 in there again. And so here is our expected. And so we'll measure that out. We'll say that our current here is larger than we expect, 2.76. We actually wanted it at 2.36. So when we measure through here, we see that that stays consistent. That's what we expect from a series circuit. It should have one consistent current all the way through. So it's a little bit larger than we expect. So let's check our voltage drops and make sure that we have a voltage drop across each of our components. 10 volts at the beginning, 9.39, so that is a loss of voltage there. 9.39 goes down to 6.63, that's a loss of voltage. 6.63 goes down to 557 millivolts, so that's less than 1 volt. So we lost a lot of voltage across that. That's what we expect. We'll keep going to the next one here, down to 171. So 557 millivolts down to 171 millivolts. So that's a voltage drop across that 140. And 171 millivolts down to 0 volts. So all of our resistors actually have a voltage drop across them, right? They just might not be accurate because we have a different current than what we expect. So we can send this out and we can actually determine what that is. We can say that we have a voltage drop across each one of these components, and that voltage drop is going to determine the current flow through here. So let's stop the circuit and we'll grab a multimeter from this top sidebar here, and that's going to allow us to measure around our components for our voltage drop. So let's measure around our first resistor and we'll see if it's actually 220 ohms by doing this. Double click on here. And when we hit play on this, we know that our current is 2.76 milliamps and that the voltage drop across this resistor is in millivolts here. We'll say that we have 607.43 divided by our milliamp value of 2.76. We're given 220 ohms, right? Those 2 milliamp are going to cancel out because of the division, and we'll be left with just an ohmic value. That's exactly what we expected from that first resistor there, so that's not the fault. So let's stop the circuit. We'll move our component forward here. Move our probe lines around the next resistor, and we'll hit play on that. That gives us a new voltage, so we'll plug that in as our top voltage here. It's now in volts, so we have to account for our millivolt value on the bottom now. So let's send this one out, and we'll say that we have 2.761 divided by 0.00276. That gives us 1,000 ohms. That's exactly what we expected from that. So let's stop this circuit. We'll move on to the next one here. Move our probe lines up by 1 resistor on both sides. And that's going to give us the voltage drop across this 2.2 kilo ohm. We'll plug that in here. We've got 6.074, 2,200. That's exactly what we expected that resistor to be as well. So let's stop this. We'll do that for the next one as well here. The 140 ohm resistor should have the smallest voltage drop across it because it's the smallest resistor in the circuit. Right, so let's hit play on this. And that is our voltage drop across. That's down to millivolts again, so we can use this one up here with our milliamp value there. So 386.5 gives us 140, right? 140 ohms. That's exactly what we expected. So let's keep going. One last one here. Move this one down to the bottom, and our positive probe can go on the top line there. And we'll hit play. 170 millivolts off of that one, so we'll plug that one in up here as our millivolt value, 170. And we get 61.59, so 62 ohms is what we actually have for that resistance. which means that that one is not a true resistor. It's not its true resistance value. It should be 680. We actually calculated it out at 61.5. So that means that that resistor is leaking, and it's probably on its way to faulting. And remember that leakage happens more often in capacitive loads. All right, but we will characterize them as resistances as well. We'll call them capacitive reactance. Okay, let us know if you have any questions.